This is what happens when you fold waveform peaks instead of clipping them. I applied 50 decibels of gain beyond full scale to a sine wave. It sounds interesting, but my other experiments with extreme wavefolding had mixed results. I built this folding patch in Pure Data, a free open-source visual programming language. You take boxes of code and connect them with virtual wires, and someday it leads to music. It's infinitely cheaper than modular synthesis, but the learning curve is even steeper, like building a computer on breadboards. I'm going through the trouble because it does things you can't do in a regular DAW. Akreel, an electrical engineer from South Carolina, makes Zen harmonic generative music in Pure Data. Autechre uses Max MSP, its proprietary cousin. But if I ever want to make music like that, I have to start simple. A wavefolder is a good start. It makes ridiculous sounds quickly. I first learned about wavefolding in Logic's Bit Crusher plugin. A bit crusher reduces the resolution of your signal, both horizontally and vertically. Logic's Bit Crusher can apply up to 50 decibels of gain, and it lets you wrap or fold the signal instead of clipping it. I wanted my folder to do two things. 1. Reflect the waveform off its upper and lower bounds, like two parallel mirrors. Logic's Bit Crusher reflects off the middle, which I don't want. 2. Take any amount of input gain. 50 dB is more than enough, but I like knowing I can push it further. I looked online for a folder that does these simple things. My first stop was a YouTube tutorial that only did the first thing. I couldn't find any Pure Data tutorial, video or text that did both. So I fell down a rabbit hole and emerged with this patch. Here's how it works. First, it makes a wave. Pure Data offers 3 wave shapes: a cosine wave, a phase ramp, and white noise. Triangle and pulse waves are too fancy. I used OSC tilde 200, a cosine wave at 200 Hz. OSC is short for oscillator, and the tilde means it's handling audio signals. I'll use an array to look at the waveform as I mess with it. The array needs a unique name. If it matches the name of another array in a different patch, Pure Data gets really upset. $0 assigns this array a unique number to avoid conflicts. To look at the wave, connect a toggle to Metro to tab right. When the toggle is on, Metro sends a signal every 100 milliseconds. When tab right gets that signal, it dumps the waveform from OSC into the array. Now we can see the wave. You probably want to hear it too. Many Pure Data users send audio to their speakers with DAC, short for Digital Analog Converter. You can't control the volume of OSC, just its frequency and phase. So plugging OSC directly into DAC makes the loudest possible sine wave. Star tilde, a signal multiplier, reduces the volume. 0.2 is a good start. I prefer output over DAC because it has volume control built in. Why blow your ears out if you forget to use star tilde? Output only works in stereo, but that's fine for most of us. Just use DAC if you have a weird audio setup. Now we can hear the wave. To fold it, you need to know the maximum volume of a signal, also known as full scale. In digital audio, waveforms are a bunch of numbers called samples that zip by tens of thousands of times a second. This array stores 500 samples, but it can store any amount. These samples are stored as bits, short for binary digits, ones and zeros. There are many ways to make numbers out of bits. Pure Data uses 32-bit floating point numbers, or floats for short. Using scientific notation, floats store very small and very large numbers in the same space. They have their flaws, but they're not important today. Floating point audio samples should stay between 1 and -1. The biggest number you can store in 32 bits is about 3 times 10 to the 38. You can send your speakers these ridiculous values with star tilde, but don't! The Pure Data manual says it clips output values above 1 and below -1. This is wrong. Apple does something else, as usual. Core Audio on macOS doesn't clip signals at all. It'll accept any value, surpassing your volume setting and overdriving the speakers. Don't try this at home. You'll damage your equipment and your ears. You can use clip if you just want to keep things bounded. I want to fold. I found this in-depth article on wavefolding from Jatin Chowdhury. He was nice enough to look at a draft of this script, so thanks. His article has many graphs plotting input gain against output gain, which is useful for studying a few audio effects. Keeping the signal untouched yields the classic y = x. Clipping looks like this. Compression looks like this, but you also need attack and release times. Applying functions to the gain of a waveform is called wave shaping. Wavefolding is a special case of wave shaping. A mathematically perfect folder looks like a triangle wave. The author of this article doesn't like triangle folding due to something called aliasing distortion. Among the basic shapes, he seems to prefer a sine wave. This is where my stubbornness kicked in. I hadn't heard of aliasing beyond fonts, but I wanted the signal to be completely untouched before it starts folding. Sine wavefolding distorts the input at every gain level. Ignoring the author's warning was a mistake. We'll get to that. In the meantime, how do you make a static triangle wave? A commenter on the folding tutorial suggested this formula. These vertical pipes are the absolute value function, which makes all negative numbers positive. The absolute value of positive 3 and negative 3 are both 3. This percent sign is the modulo operation, mod for short. It's the remainder of a division. 7 over 4 is 1, with 3 left over, so 7 mod 4 is 3. 11 over 4 is 2, with 3 left over, so 11 mod 4 is also 3, and so on. expr tilde is good for equations like these. Pure data is written in C, the oldest commonly used programming language. The expression syntax is C-like, which will become annoying shortly. I checked this person's formula in Desmos, Wolfram Alpha, and Python. I didn't check it in C because then I'd have to remember how to use GCC. Boring. All 3 tests looked fine, so I wrote this expression. Abs is short for absolute value. C has a percent sign modulo, but it only works on integers, so I had to use fmod instead. I fed the wave through this expression and, what? Troubleshooting this was a mess. Luckily, I can show you how I should have solved it. After checking for typos, either abs or fmod must be broken. Examining the 2 functions separately reveals that abs works fine and fmod doesn't. I never told you how modulo handles negative numbers because it depends. If you're a modern, popular math tool, you think of modular arithmetic. -1 mod 4 is equivalent to 3 mod 4, and it's often better to just call it 3. If you're an ancient programming language, you figure it's fine to return the same sign as the dividend, so you do that for at least 37 years. In C, you can write a passive-aggressive function called cmod, correct modulo, that adds the divisor to fmod when it returns a negative number. But this isn't C. I want a one-line pure data expression. A reference page on fmod brought me to another function called remainder. Its output is weird, but it's the same on positive and negative numbers, and it actually changes signals in pure data. I messed with the constants until it worked, a classic trick. That's my patch. It's time to test it. With the 3 basic wave shapes, I'm sweeping the gain from 0 to 50 dB over 10 seconds. Why isn't this number 50? Honestly, the reason sucks. I'll just put the math on screen while I test this patch on white noise. Well, that's underwhelming. Digital white noise assigns a random number to every sample. This is what we call garbage in, garbage out. You heard the sine wave test at the beginning of this video. The closest I got to making music in pure data was turning this patch into a wavetable synthesizer. Wavetables let you squash, stretch, and loop tiny fragments of sound to make interesting textures. One of the 4 sound channels on the Game Boy is a wavetable. I've had fun playing with it in Little Sound DJ. Pure Data has tab osc4, which turns an array into a wavetable. I'll walk through my little synthesizer quickly. This is the original folding patch with a couple of changes. First, the frequency is different. For boring technical reasons, the waves period should be a power of 2 samples. I chose 512. The sample rate is 48 kHz. I derived the frequency using dimensional analysis, an old science class trick. Divide 48,000 samples per second by 512 samples. The samples cancel out, and you get 93.75 inverse seconds, better known as hertz. Second, Metro triggers a message to reset the phase of the oscillator. I want both ends of the wave at 0 so they don't jump around when I apply gain. The message is 0.25 because a sine wave is a quarter cycle off from a cosine wave. I know saying cosine wave earlier sounded weirdly pedantic, but the phase difference is important. This section applies a random gain 8 times a second. It uses sample and hold, which I first used on the ARP 2600. Every time this phase ramp drops down, samp hold takes a sample from the white noise and holds it until it sees another drop. I can make a whole video about sample and hold. Finally, this section makes a random note on every 10th gain change. M to F converts a MIDI note to a frequency which feeds into tab OSC4. I also use the phase ramp as a crude amplitude envelope. The note starts kind of loud and ends kind of quiet. Here's how it sounds. It's not much, and I can hear it clicking, but it's got potential. I got a lot out of sine waves. How about a sawtooth wave? Looks like it became triangle waves and then wrapped around the universe. That wrapping is aliasing. I need to talk about it because it's about to ruin our day. The highest pitch sound in digital audio alternates between two numbers on every sample. Its frequency depends on the sample rate. At 48 kHz, it makes a triangle wave at 24 kHz. I won't play that in case you're an infant or a dog. This is the Nyquist frequency, and it's always half the sample rate. Beyond that, you get aliasing. To demonstrate the effect, I have two waves plotted across 10 milliseconds. The white wave takes 40,000 samples a second. The pink wave only 4,000. At 200 Hz, they're both doing all right, but the pink wave has jagged edges. What happens as we approach 2 kHz? Around 18 or 1900 Hz, the wave appears to dip up and down. This looks like beating, the wah-wah effect with two waves at close frequencies, but digital analog converters are smarter than this diagram. Any useful DAC applies a low-pass filter at Nyquist to reconstruct any peaks living between samples. It's called the reconstruction filter. In our case, it derives the white wave from the pink one. At 2 kHz, the pink and white waves both have 20 peaks. Beyond Nyquist, at 3 kHz, the white wave has 30 peaks and the pink wave has 10. Unlike the false beating from earlier, a low-pass filter can't triple the frequency of this wave. As we reach the sample rate, the number of peaks slowly go down to 0. Then the cycle continues. 6K is 2K, 8K is 0 again, and so on. Frequencies reflect into lower frequencies, then back up again. That's aliasing, and that's why we heard the sawtooth wave wrap around. The pink wave aliases at pretty low frequencies, but the white wave holds strong up to 20 kHz. Higher sample rates avoid aliasing for longer. I didn't know any of this when I plugged my guitar into this patch. You're about to hear an unpleasant sound, but I'll turn the volume down and filter it heavily. For reference, this is regular clipping. The tone is basic, but it's normal, distorted guitar. Here's the same guitar fed through the wavefolder. Wait, stop. What the hell is that? Let's talk about overtones. You might know that every sound is made of sine waves. I even made a video about it. Most sounds have a fundamental frequency, the lowest sine wave, and overtones, every wave above it. Pitch sounds, like guitar, neatly arrange their overtones along integer multiples of the fundamental. Folding a sine wave creates a bunch of overtones. Folding another sound multiplies that effect across every sine wave. The higher the frequencies, the more aliasing you'll get. There's no guarantee that overtones slot into integer multiples when they reflect off Nyquist. We were lucky with the sawtooth wave. Some overtones got quieter. My guitar made these irregular, obnoxious peaks. Even with a filter, they're excruciating. They feel like Q-tips made of fiberglass insulation. But there's still hope. Folding doesn't affect white noise, so a noisier sound might be less obnoxious. Drums and cymbals have overtones all over the place, nowhere near integer multiples. So I tried a drum beat. A couple years ago, I made an instrumental to play with deliberately ugly, trashy sounds. It's built around this beat. I fed it through the wavefolder at various gains. I liked it best around 30 decibels. Here's how that sounds. It's like if robots could sneeze. But against the guitar, it's almost restrained. I'm starting to think there's a reason I couldn't find a triangle wavefolder in pure data. You have to be careful not to damage your ears. You have to learn more about aliasing than many musicians ever need to know, and you have to understand a quirk of the standard math library in C. Remember when Mr. Chowdhury suggested folding with a sine wave? Not only does it cause less severe aliasing, it's easier to implement in pure data. To apply a sine wave with a period of 4, you write sine of x times pi over 2. It causes a little distortion up front, but you get less pain at higher gain. Turns out, mathematical perfection isn't always good. I'm broadcasting from a secret location to say that I've launched a Patreon. If you'd like to support this weird little channel every month and you can afford it, that's the place to go. You get a couple perks and you'd help me justify the substantial amount of work that goes into these videos. If you really hate monthly payments, I'm still happy to accept donations on Ko-fi, but the perks are Patreon only. Arigatou gozaimasu.